Now that we have coordinates for 30, 45, and 60-degree angles in quadrant 1, we want to move those angles into the second, third, and fourth quadrants with reference angles. A reference angle is measured from the terminal side to the nearest part of the x-axis. As you can see, we've put a 60-degree reference angle in quadrant 2, 3, and 4. So if we have 60 degrees between the negative x angle up to the in the second quadrant, that'll be the same as a 120-degree angle. If we have a 60-degree reference angle in quadrant 3, we're talking about a 240-degree angle. It's 200 between 240 and the 180 is our 60 degrees. Over in the fourth quadrant, the nearest x-axis is the positive x-axis. So we are 60 degrees before 360. That's 300 degrees. So 60, 120, 240, and 300 all have 60-degree reference angles in quadrants 1, 2, 3, and 4. The next thing we want to do, once we have figured out our 4 angles with those reference angles, we want to figure out the coordinates of each of those points on the unit circle. For 300, we could see it's directly under the 60 degrees, so we're going to have the same x-coordinate of 1/2. The y-coordinate, because of the symmetry in this unit circle, is going to have a value of √3/2, just like at 60 degrees, but we're going to be in the fourth quadrant where y is negative. So it all lines up. Down here in the fourth quadrant, x is positive, y is negative. So x is positive, y is negative. So let's take these 3 angles and put them in all 4 quadrants, figure out what the angle measure is between 0 and 360, and figure out the coordinates. But first, a word from our sponsor. Welcome back to Leach's Garage, the dumbest trigonometry channel on YouTube. So what we're going to do is we're going to take the 30, 45, and 60 and place those angles in all 4 quadrants. We already had 60 done. I should have taken the time while my sponsor was going over my sponsorship. I don't have a sponsor. That's why there wasn't anything happening. We know that this angle is going to be at 120 degrees. From 1/2, we'll drop down to get our 240-degree angle. And let's see, I'm just going to go straight across, drop down from 1/2. There's our 300-degree angle from the previous page. So we also want to have a 45-degree angle in the second quadrant, a 45-degree angle in the third quadrant, and a 45-degree angle in the fourth quadrant. So if we have a 45-degree reference angle in the second quadrant, what angle is that? If I measured from the positive x-axis in standard position, what is this angle? 135. And then in the third quadrant, what is our 45-degree reference angle? 225. And in the fourth quadrant, what's our 45-degree reference angle? 315. Makes sense. 60 is 15 degrees off 45. And so our new 45 is 15 degrees off our 60-degree reference angles. So now I need the 30. So I'm going to go to the 1/2 on the y and connect up my unit circle. So I can have nice proper placement. I'm going to go 1/2 on the y. So what's a 30-degree reference angle in the second quadrant? 150. What's a 30-degree reference angle in the third quadrant? Awesome. And a 30-degree reference angle in the fourth quadrant. These are all angles that we will want to recognize, along with 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Oh, and back up to the beginning at 300 with 360 degrees. These are our iconic triangles spread out over the unit circle. We also wanted to get the coordinates for all these points. Remember, for 30 degrees, at 30 degrees, we had a √3/2 on the x and a 1/2 on the y. For 45, we had √2/2 and √2/2. And for 60, we have 1/2 and √3/2. At 0 and 360, let's fill in all these things. At 0, we've got the point 1, 0. At 90, we've got the point, where am I going to write it? 0, 1. At 180, we've got the point -1, 0. And at 270, we've got the point 0, -1. The one we filled in before was 300. So let's go through the fourth quadrant. So the 300, our x coordinate was positive 1/2, but our y coordinate is negative. Notice that the signs have changed because the quadrants changed, but the values haven't changed. The 300 has a 60-degree reference angle. What are the coordinates for our 315? √2/2 and -√2/2. And what are our coordinates for 330? Notice that the values √3/2 and 1/2 are the same, but the signs are different. The absolute values are the same, but the signs are different. The absolute values are the same because they're the same reference angle, but the quadrant is different, and that changes the signs. The reference angle gives us the values. Quadrant gives us the signs. The reference angle gives us the angles or values. The quadrant for the sign, not the SIN sign, the SIDN sign. Positive. The other thing that we noticed is that the x coordinate was always telling us about the cosine of the angle, and the y coordinate was telling us about the sine of the angle. So at that 330, with those coordinates being √3/2 and -1/2, we know that the cosine of 330 is √3/2, and the sine of 330 is -1/2. We get the values from the 30-degree reference angle. When we see that 330-degree angle, we immediately think of a 30-degree reference angle. So cosine of 30 is √3/2, sine of 30 is 1/2. And we say the 330, we think the 330 is in the fourth quadrant. So the cosine is positive and the sine is negative. In the fourth quadrant, it makes sense that cosine is positive because cosine is the x and x is positive in the fourth quadrant. And it makes sense that the sine is negative because the sine is y and y is negative in the fourth quadrant. All you have to do is remember all of these values for sine and cosine all the way around the circle. It only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. But there aren't actually a lot of numbers running around. Because if you remember the principles behind where these numbers come from, then it'll be easier to organize. So if I say something like 120, you immediately think of a 60-degree reference angle in quadrant 2. That's a lot of information. 60-degree reference angle in quadrant 2. So if I said something like, what's the cosine of 120 degrees? You know, in quadrant 2, it was 60 degree. Cosine of 60 is a half, but in the second quadrant, it's negative. So cosine of 120 is negative 1/2. You just want to learn all this in all these patterns so you can put the values together quickly. It's not because you're going to be on a desert island doing trigonometry without a calculator, because if you're on a desert island, you have bigger concerns than trigonometry. I've never understood that argument ever. Like, what if you're on a desert island and you want to do some trig? I'm like, if I'm on a desert island, I want to find water, shelter, food, and some coconuts so I can build a radio. I saw Gilligan's Island. I know it's possible. I don't know. I watched some YouTube videos and they never like bring up trig. They always just like tie a bunch of twigs together. And then like the next scene is like a full-on house. You know what I'm talking about? Like those guys standing on a patch of dirt and they have like a crowbar and they build a pool. It is, they're not necessarily on the same plot, but they are kind of nearby each other. And if you see video of like those fancy pools, like a couple months later, they just get kind of sad. Really. So that's not the point. If we don't learn the values and we can't figure these things out quickly, it gets in the way of everything else. One of the reasons that we struggle with algebra is that we don't really have a solid foundation in arithmetic. Yeah, we can do some things, but it takes us too long. I like to think about parallel parking. Parallel parking is not really a skill that you absolutely need to have. It's convenient to have, but you can probably get away without knowing how to parallel park. If it takes you 45 minutes to parallel park, I'm sorry, you can't parallel park. That isn't how parking is supposed to go. You're supposed to spend 45 minutes looking for a spot and then park in like 10 seconds. Like one shot. It's like back in and then done, right? If you're like 45 minutes looking for a spot and then 45 minutes to park, dude, you just like park somewhere else. Maybe you should just walk. I lived in San Francisco for a while, so I had to become kind of proficient in parallel parking. I'm just kidding. I had a parking space. I would pull into my garage and then walk outside and flip off all my. So it gets in the way if we don't remember these things. So we want to move quickly and utilize these. We want to start eventually stretching these out to sinusoidal functions, modeling things that go up and down. And we don't want to get to the point where I go, well, where are the halves? It's a cosine. Where are the halves? The halves are at the 60-degree reference angles. We want to know these things right away. Just like if we're doing some math problem, some algebra problem, I go, what's 7 times 8? And you're like, oh, hang on. And you pull out the calculator and I'm like, hey, Siri, what's 7 times 8? I mean, it just gets in the way. It was rhetorical, Siri. Chill. So it gets in the way and it slows you down. And by the time you figure out that it's 50, whatever it was, the problem has already moved on. Like there's like a moment where you had the problem right in front of you. And that not knowing that it was 7 times 8 was 50, whatever it is, got in the way and kept you from understanding what was going on in algebra. Compounded with the fact that no, your algebra teacher probably didn't say, hey, remember arithmetic? All the operations here are just arithmetic operations. Has everybody been told that? Algebra is arithmetic. There's nothing new in algebra that you didn't do in arithmetic. We all know this, right? Have I multiplied 23 times 17 for y'all? This doesn't need to be in the video, but I don't edit videos. All right. Think back to the algebra what you were taught. Think back to the algorithm that you were taught to multiply 23 times 17. Now, I want to dismiss any argument that the fast way to do it, because there is a fastest way to do it. Hey Siri, what's 23 times 17? That wasn't it. 23 times 17. 391. That's the fast way of doing it. Grab a calculator. So I want you to think back to the algorithm that you learned when you were a child, and we decided we were going to program you. But it's disrespectful. It was disrespectful, by the way. We decided we were going to program with you with an algorithm like you're some kind of computer. So disrespectful. You're a fucking human being. And here we are trying to program you with an algorithm. I want you to think back to your memory. Think back to how you learned to do this. Some of you are thinking the following. The first thing that you do is 7 times 3. Who is thinking 7 times 3? Whose first thing that you did was 7 times 3? The rest of you may have been taught competent arithmetic, but for the most part, the first thing we learned was 7 times 3. Now the fun part. How do you write it? You put the 1 down here, right? And where do you write the 2? Are you fucking kidding me? You want to know why people are bad at math? This is a start. What would you say next? Where's the 14 come from? What 2 are you talking about? That's not a 2. I see no 2s. There are no 2s here. I don't see any 2s. What's this number up here? What's this first number that we have? It's what? Just read it. What is it? It's 23, right? 23. 23. What is this 2 right here? It's not 2. That's 20. What's this 2 up on top? No, that's the 20 from the 21 because we wrote it in this fucked up way. Everything's all out of order. Are you fucking kidding me? It's no wonder that people hate math because this is what we teach them to do. Well, there's no trick to it. It's just a simple trick. Nothing up my sleeves. Voodoo. All right. 7 times 20 is how much? 140. 140 plus 20 is how much? 160. That's why it makes sense to put the 16 here, because it's not a 16, it's 160. There's a 0 where that 1 is sitting, and 0 plus 1 is 1. All right, now for the next question. You might be primed to answer this wrong. What's the next thing you're going to say? 10 times 3. See, some of you learned already. It's like, oh, no, I don't want to get yelled at again. And you know that the 1 and the 17 represents 10. So 10 times 3, how much is that? 30, right? So how many of you are leave a space here? And how many of you are put a 0 here? Who's on team put a 0? Put a 0. Put a 0 there, right? Who's on team leave a space? I need to know who your fucking math teachers are. Why leave a space? Because, yeah, it keeps you from writing things. But if it's a fast thing that you want to do, we've already got the fast way. We reach over, get our calculator. By the time I get through this explanation, we already have it's 391. The space is there because it should be a fucking 0, because 10 times 3 is 30. And we draw it that way because 30, 3 in the tens column, 0 in the ones column. I'm not making fun of any of you. I'm making fun of all your training. It's just for fun. So don't feel like I'm coming down on you. Please. It's just a show, right? I'm not actually angry. I know it's probably that's the problem when math starts acting angry. It's like natural reaction. It's like, oh, no, I have trauma surrounding this. I can't have math teachers be all fucking angry at me. That's like the source of the trauma. You know what I mean? And it's like you have all this trauma of surrounding math teachers because math teachers get angry because you know how to do stuff when it's like literally their job to explain shit to you. You know what I mean? Man, messed up what we've done to you. That's why here I like this class because y'all are adults and I could say, hey, remember that trauma? Yeah, let's try to deal with that trauma. But you already have the trauma. I don't inflict any trauma. It's an entirely new trauma that I mean, it's not trauma at all. We do 10 times 3 and it's 30, so that's why that goes there. And then we do now you're not going to do like 1 times 2. It's going to be 10 times 2, and how much is that? 10 times 20. How much is 10 times 20? 200. That's why we put the 2 here, because this is the hundreds column, and then we can add 391. Dope. All right. Now for algebra. Remember algebra? Everybody remember algebra? Is everybody having trauma? Trauma response? Oh my God. Algebra. You're like, oh, fuck that. How many of you think when I say the word algebra, the first thought is you think of, it's like, ah, through you, Mr. So-and-so, whoever was your algebra. That's the person that traumatized you. They're the physical embodiment, the human representation of all that algebraic nonsense that you had to do. What do you do for this problem? I'm thinking of a four-letter word and it starts with F. Foil. Rainbow? Is rainbow like 2xx? Yeah, that's the same. Rainbow is just a nicer way of saying foil. So how many of you learned so you do 2x times x, right? Oh, rainbow is dope. So then 2x times 7. And then what? 3 times x. See, I always drew them. We were taught to draw them down here, so we didn't get to draw rainbows. And then 3 times 7. So 2x times x is 2x squared. 2x times 7 is 14x. 3 times x is 3x. 3 times 7 is 21. Oh, and then what can we do? Combine like terms. What are the like terms? (14x) and 3x is 17x. So how many of you were taught FOIL for 2x plus 3 times x plus 7? Who remembers FOIL? Were you told to do FOIL on this? How many of you would do FOIL on this? Why not? Because this is numbers and this is polynomials, right? What's the difference in the procedure? None. It is the same thing. You can multiply one just like the other. Because the 2x plus the 23 and the 17 is 23 and 17. And we're multiplying these numbers. 20 times 10 is 200. 20 times 7 is 140. 3 times 10 is 30. 3 times 7 is 21. Those are the same 4 numbers what we came up with down here for this 391. There's the 2 for the 200. There's the 3 for the 30. There's the 21 right in a stupid way with the 2 up here and the 1 down here. And then the 16 doesn't show up because the 140 and the 20, we organize it that way. Oh, we'll take the 20 from the 21 and put it on this term here with the 140. So annoying. Especially because it just erases what's going on in multiplication. This is just distributive property. Multiplication distributes over addition. And that means that each term in one number gets multiplied, or each term in one polynomial gets multiplied by every term in the other polynomial. Just like each digit of one number gets multiplied by every digit of the other number. Now, if I take this 22x plus 3 and x plus 17, I make x equal to 10. What is this first number equal to? 23. And I make the x equal to 10 over here, and what do we get? And 23 times 17 is how much? 391. So we get 200, 170, and 21. How much is that equal to? 391. Polynomials are just numbers, but with x instead of 10. Polynomials are just numbers, but with x instead of 10. And that is the tragedy of American algebra. The fact that I can multiply these two things and a whole bunch of people are like, oh, not seeing them as the same. Not blaming you. You were most likely not given the opportunity to see them as the same. Any questions? Anyway, so my colleagues know better than asking, man, why are our students not very good at algebra? Well, you don't spend a lot of time teaching them algebra. You just spend a lot of time punishing them for making mistakes instead of encouraging them to make mistakes. That makes sense? Don't punish people for making mistakes. Encourage them to make mistakes, because that's how we learn things. I don't know, maybe I'm wrong. Maybe we should make the people feel bad for making mistakes. But all it does is create a bunch of students that are afraid of making mistakes. I don't want anybody to be afraid of making mistakes. I want you to be boldly well let me. It's like, oh, 3 times 5 is 8, right? I'm like, oh, no, 3 times 5 is 15. And you're like, oh, well, shit, how did that happen? Well, I don't know. Sometimes our brains say, fuck you, we're going to get it wrong. That's just what happens. I mean, sometimes you're like, oh, and you go over the problem right away, and your brain is still thinking, oh, dude, it's still working. And you're like, ask your brain 3 times 5, it's like, well, 8. You're like, why is this not working? What's 3 times 5? 8. And you're like mad, you throw the book across the room. Then you come back 20 minutes later, and you're like, oh, 3 times 5 is 15, now it's working. Because your brain got bored and moved on. You know what I'm talking about? So you can't be afraid to make mistakes, especially some of you might be going into science. And if you're going into science, you absolutely have to embrace making mistakes. If you're going into science, you're going to spend most of the time being wrong. You're going to come up with a hypothesis, like, well, how about this? No? Okay, how about this? No? Okay, how about this? No? How about this? Yes, now you're a genius. You got 1 out of the last 300 trials to work, and you're like, well, now you're a fucking genius. That won't work. You know what I mean? You didn't learn one way to do something. You learned 299 ways to not do the thing. And then you pass that knowledge on. That makes sense? That's what I want you to think about between now and Thursday, while you're easily just assimilating all this information and looking for those patterns. Let's take all that, look for those patterns, try to put this whole circuit together. Be able to recreate the circuit with all the details just by knowing those patterns. Get things wrong is totally okay. No one should make you feel bad for them. But while you're doing this, while you're learning these patterns, I want you to think back to the times where someone in a position of authority made you feel bad for not being very good at math, and find a way to let that go. Everyone here is perfectly good at math. Perfectly good at math. There's nothing that's physically going to stop you from learning math. Nothing is physically wrong with your brain. Nothing will physically stop you from learning math. Math only wants your time and attention. All we have to do is make your brain ready for that. And the first step in that is kind of looking at our trauma and say, this is trauma that we have. I'm going to find a way to move past this. I'm going to feel okay about making a mistake. Is that cool? Do we agree? If you're not sure what to do, take a problem and fuck it up. Be like 23 times 17. It's 2x squared plus 21. Nah, I got it wrong. 23 times 17. 2 times 10 is 200, and 3 times 7, 221. See, it works out the same way. And then recognize what you're getting wrong. Any questions? Comments? Deep thoughts? All right, that's it for today. Learn the unit circle for Thursday. That's it for today. I'll see y'all on Thursday. Everybody have a good couple days. And thanks for playing.